Thermochemistry. I pray when you read or hear this word, you think heat. So we studied thermochemistry in chapter 6, and we need to just bring to mind whenever we're dealing with heat that we're usually talking about enthalpy. Enthalpy, remember, symbolized by a capital H, is heat at constant pressure, which is usually what we are pursuing in a lab situation. Thermochemistry is wonderfully practical because we want to know how much energy do we have to invest to get a reaction to happen. And remember, those are endothermic, so the overall process change requires the input of energy. So the change in enthalpy will be positive. Or how much heat does it release to us? And then we can use for further processes or so on. So we, with heat, are usually investigating enthalpy. Remember, enthalpy is represented by a capital H. It is a form of energy. Most commonly, we see kilojoules as our unit, but we can also be in joules. And there are 5 different ways that we can analyze heat that is either required or released in a chemical process. All right, we're going to go through calorimetry, how we can determine how endothermic or exothermic stoichiometrically, remember those enthalpies of formation, Hess's Law, and bond energies. So let's go through each one. Okay, starting with calorimetry. Well, I pray that we just know calorimetry will be synonymous with this very, very famous specific heat equation. So Q, of course, is our heat. M would be the mass of the entire substance. Okay, how do we know if it's employing calorimetry? Well, usually we are using a calorimeter, which is a special device that is a good insulator. So it won't release heat or absorb heat in and of itself. And most practically, that is just a coffee cup or a polystyrene cup. So if the question reads something like a polystyrene cup was used or a coffee cup calorimeter, we know we're using calorimetry. And we're doing the reaction or the physical process like dissolving in the calorimeter. So the mass will be everything inside of there. The specific heat will be the combination of what's in there or what is experiencing the temperature change. Most often, we are doing a reaction where our reactants or the species we're looking at are in aqueous solution. So usually, the specific heat of the solution, aqueous, will be very similar or very close to the specific heat of water. Because it's usually water that's undergoing our change in temperature. And remember that water has a specific heat of 4.184 joule per gram degree Celsius. Specific heat, remember, is the amount of energy that must be invested to take 1 gram of your substance to increase that 1 gram 1 degree Celsius. Okay, just be very, very careful about your signs, because of course if the water is undergoing an increase of temperature, that is because the process is releasing the heat. And so from the perspective of what's inside, we'll get a positive Q. But how did it increase in temperature? The reaction released it. So remember, with thermodynamics, we are given permission to change sign whenever we understand it needs to be different. Okay, stoichiometrically. Well, we could be given a balanced equation and be told the enthalpy change of the reaction. Let's remind ourselves what it means when we have this floating zero. That means we are at standard state, not STP. STP is with gases. Standard state are room conditions. 25 degrees Celsius, approximately 1 atmosphere of pressure, and if we're dealing with a solution, the concentration will be 1 molar. All right. This is the amount of energy that will be released, it's exothermic, per mole of reaction. So that means, per the balance equation, that means we will get out 84.68 kilojoules for every 2 moles of carbon, understanding that we would have a plenitude of hydrogen. I'm going to go ahead and make that negative to remind myself that that's being released. But that would be the same amount per 3 moles of hydrogen or 1 mole of the C2H6 product. If you could, of course, see, these can then be used as conversion factors. So you may be asked, well, what is the amount of energy that would be released if you reacted, let's say, 20 grams of carbon? Well, we can just use this relationship. So we know carbon's average atomic mass is 12.01 in every 1 mole. And we're given this information that for every 2 moles of carbon, we get 84.68 kilojoules. And so stoichiometrically, if we're given this information, it's per the balanced species. All right. Enthalpies of formation. All right, we need to know what this is. So if you would choose any substance, what comes to mind, let's say potassium fluoride. All right, if I want to make 1 mole of this, and I want to make 1 mole of it, and we know ionic compounds are going to be solids at room temperature and pressure, and I'm going to make it out of its elements. Now we know potassium is not diatomic. It is found as a solid at room temperature and pressure, but fluorine is diatomic and it's a gas at room temperature and pressure. If I just want to make 1 mole of this, I need 1/2 mole of my fluorine. If I would do this, I'm starting with the elements in their reference form. So what is the most stable or lowest enthalpy of these substances? They would be the form that's of lowest enthalpy or lowest energetically, combining them to make 1 mole of product. So I could call that enthalpy of reaction, but if I'm making 1 mole of it from its elements in their reference forms, then it is the enthalpy of formation. And if I start at standard state, then I get that floating 0. If I would make 2 moles of it, and then 1 and 2 coefficient, it's not enthalpy of formation. It would just be enthalpy of the reaction. So if I look at, for example, making carbon dioxide gas, well, I know to make 1 mole of this, out of its constituent elements, carbon and oxygen. Oxygen is diatomic. We know it's in the gaseous state. Carbon. Remember, there's different allotropes of carbon. Graphite is the lowest in energy. And look at that. I just need 1 mole and 1 mole to make 1 mole. And if I would do this, that would be the enthalpy of formation of carbon dioxide gas. Well, what if I want to make O2? Well, I would make that from its constituent elements in their reference form. And so remember, the enthalpy of formation of elements in their reference form is 0. So for oxygen, for hydrogen, for fluorine, for potassium, for sodium, for, we could just keep going on and on and on and on. We know these enthalpies of formation are 0. All right, we need to have a good, firm understanding of what enthalpy of formation is. But then how do we apply it to get how endothermic or exothermic a process is? Well, we can get the enthalpy of the reaction. I get to make my favorite math symbol. We would take the sum of the amount of moles of the enthalpies of formation of product minus the summation of the enthalpy of formation of reactant. So of course, we would have to be told what these enthalpies of formation would be. So for example, there's our equation. Remember, Nimsey calls it the Big Mama equation because we rely on it a lot. So if we would be looking at this equation, we would get the enthalpy of the reaction by summing up the enthalpy of formation of product minus reactant. So we would have 1 mole of the Al2O3 solid, and the enthalpy of that formation is negative 1676 kilojoules per mole, so you can see how the moles cancel, plus 1 mole of aluminum chloride times the negative 704, and on and on and on and on, yeah, and then you'd subtract from that 3 moles of aluminum. Oh, we're not given an enthalpy of formation. Oh, we need to know that's 0, and then on. Yeah, so we'll do an example that applies this, in preparation. Okay, for the AP test. So that was enthalpy of formation. So next, the 4th is Hess's Law. Okay, Hess's Law, because enthalpy is a state function, if you are given an overall equation and then many reactions with their enthalpies of reaction, can we manipulate these to get the overall equation? And we definitely can. You won't ever have to come up with these. We just have to show how we would manipulate these. Now, the manipulation that you do to the equation is the same manipulation you apply to the enthalpy. Because remember, these are per mole of your balanced equation coefficients. So if you're changing these, or changing the direction of the reaction, these are going to change. I would use the overall reaction as my, kind of director. And if I see I need 1 mole of C2H6 gas. So this equation gives me 1 mole of C2H gas, but it's as a product. So I need to make this a reactant. I need to flip this equation. So C2H6 to make 2C solid plus 3H2 gas. And when I flip an equation, what was exothermic will then be endothermic. And so the enthalpy will be positive 84.68 kilojoules per mole. All right. Next, I need 7 halves of O2. Oh, well, this equation has O2 in that, so I'm going to move on to my CO2. And my second equation gives me CO2 product, but here I have 2 moles. Here I only have 1. So I can apply the coefficient of 2 through the whole equation. So this will give me 2 carbons and 2 O2 gas, yielding 2 CO2 gas. And if I increase these by a multiple of 2, then this would go up a multiple of 2. Sign remains the same. All right. And then I need 3 moles of H2O gas as product. So I see I need to multiply this through by 3, but not reverse. So I have 3 H2 gas plus 3 halves O2 gas yields 3 H2O gas. And then I would multiply this by 3. All right, let's make sure that everything tallies to give the overall equation. Okay, like species on the product and reactant side cancel, so that would cancel that. This cancels this. Okay, so I have my C2H6. Ooh, what do I do here? Well, I would create a fraction. And look at that. There's my 7 halves of O2 gas, yielding 2 CO2 gas plus 3 H2O. And that, as I added to get the overall equation, I would just add these to get the enthalpy of the reaction. That is the application of Hess's Law. All right, so 5th, bond energies. All right, just like enthalpy of formation, we need to understand what bond energy is. And bond energy is the energy that is required to break a chemical bond. These are always positive values, always. To break anything, it requires the investment of energy. So, the equation is a little different. To get the enthalpy of the reaction, Okay, what we're going to do is sum up the bond energy of reactants and subtract the bond energy of products. Okay, usually thermodynamic equations, like applying the enthalpy of formation, it's product minus reactant. But this is our only one, that's reactant minus product. Now, ladies and gentlemen, you are given these on the equation sheet, so you can rely on them and go back and just make sure you're doing it correctly. So if we would look at this reaction, so we have to understand, okay, what is being broken and what is being formed. So we can sketch out quick Lewis dot structures. We can see that to make 2 moles of HF, we're going to have to break these 2 bonds, and if we're given their bond energies, we would simply take 1 mole of this plus 1 mole of this, and then subtract. Do you see, we have to break 2 moles of HF single bond. So it's just recognizing, okay, what new bonds are being formed and what bonds are no longer there, they must be being broken. So we would simply then, to get the enthalpy of the reaction, just add up 1 mole of the HH single bond, 432 kilojoules per mole, plus 1 mole of the fluorine-fluorine single bond. And again, it's reactant minus product. And you see the bond energies are always positive. Always, 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 always. And then 2 moles of the HF single bond, and that's 565 kilojoules per mole. Now, a lot of times you are given the enthalpy of the reaction, and then you're given maybe 2 of these, and then asked to find the bond energy of something else. Be very, very careful, because often when the College Board is asking you to find bond energy of something, you'll have multiple of those. So it's not just solving for bond energy, it's making sure that you recognize that this term is multiplied by a factor of 2. So you'll have to divide out, this will ultimately be 2x whenever you get your algebra solved. So to find this, you'll ultimately have to take your kilojoules and divide by 2. Okay, so that is, a walkthrough of all the ways that we can find heat or the kilojoules involved, either exothermically or endothermically. All right, I'd just like to take a look at just one combined problem. So it's absolutely up to you if you want to skip to where I have the answers. All right, ladies and gentlemen, so we want to make sure that when we're dealing with a free response, we don't overlook any given information. All right, so force yourself to slow down and read. Magnesium flakes were added to an open polystyrene cup. So, we know we're using calorimetry. So as soon as we see that, what should come to mind is